Lesson 2, we talked about the second of the transformations, that's isometries, and this time we're talking about reflections. And so we got 2 learning targets. Number 3, draw the image of a reflection or write a rule for the reflection. So very similar to what we did with translations. And then learning target number 4, prove that a reflection is an isometry. So essentially, we're going to give you one proof here, and you're going to have to be able to know that one proof. All right, so let's start talking about reflections. What is a reflection? Well, if simply put, a translation was like a slide or a glide or something like that, a reflection might simply be put as a flip. Okay, you're flipping something over a line of symmetry, and so if this is our line of symmetry, and we have something like a triangle over here, okay, well, we would be flipping it over this line of symmetry, and so it'd be kind of like folding it over a piece of paper or something like that. So this is a reflection. And there are 2 essential properties that you're going to need to know about a reflection. And that is, when you reflect something, okay, let's call this A, and let's call this A prime. So this is the new one, this is the original image. Okay, and let's call this point right here R for reflection. Okay, well, 2 things that we need to know. Number 1, and that is AR is going to be congruent to A prime R. And so these 2 things are congruent. They are the same distance from your line of symmetry. Okay? And then let's call this line of symmetry, we'll call it line L. Okay? The other thing that you need to know is that L, that line of symmetry, is going to be perpendicular to the line A prime. Okay, and so this line right here that's created when you reflect that is got to be perpendicular to your line of symmetry. And so these are 2 things that we're going to need to know, especially for that proof. All right, tips on the grid. So when we're reflecting things on the Cartesian coordinate grid, there's going to be just some tricks in general that will help you out with some of the common reflections. So one of the common lines that we would reflect over would be the x-axis. So let's just take any random point here. We'll say 5, 2. We'll call this A. Okay, if we start out with 5, 2, and reflect this, well, over the x-axis, well, you can see that when we reflect that, we'll call this A prime, well, we're at 5, negative 2. And so the numbers have actually stayed the same. It's just that the sign has changed on the second one. And so here we'll call this the x-axis. In general, what we could say is if we had any coordinate xy and reflected it over the x-axis, that would turn into, you'd have the same numbers, x and y, except that we would just change the sign on the second one. All right, well, let's talk about the y-axis now. It'll be another common one. So here's the y-axis, and, well, let's see, if I start at 5, 2, well, if I reflect it over the y-axis, I'd be over here at negative 5, 2. So 5, 2 turns into negative 5, positive 2. And so hopefully you can see that the numbers have stayed the same, but the sign has changed on the first one. And so we can just go ahead and say, in general, for any point, the numbers are going to stay the same, x, y, except that the sign will change on the first one. All right, another of the common lines that you will reflect over is this line right here. This line would be the line y equals x. It has a slope of 1, up 1 over 1, and it has a y-intercept of 0. You see, at least I tried to get it to go through the origin. Well, when we reflect over this line, 5, 2 becomes, well, 2, 5. You can see that my 2 properties here, stay true. This distance is congruent to this distance, and they are perpendicular. And so this is an example of a reflection. So when I'm reflecting over the line y equals x, okay, well, 5, 2 turned into, well, 2, 5. And hopefully you can see the pattern here. In general, any regular point, xy, would turn into, well, the signs didn't change, but we just switched the numbers. 5, 2 becomes 2, 5. You just kind of flip them. So xy, whatever was in the y spot, would go first, and whatever was in the x spot would go second. All right, so these are some tricks for you to use on the grid. All right, so the notation that we're going to use looks like this. So if you see the capital R, that implies reflections. You'll have a sub thing here, and that's going to tell you what line to reflect it over, and the thing that's in parentheses is what we are reflecting. And so, in this case, point F is what we're reflecting each time, and point F is at 2, 6. 2, 6 would be right here. All right, so if we reflect over the x-axis, remember we keep the numbers the same, but we go ahead and change the sign on the second one. So we have 2, -6, and you can see that right here would fit. All right, and then if we reflect over the y-axis, remember that the numbers, again, stay the same, 2, 6, but this time we're going to switch the sign on the first one. You can see that fits pretty well right there. All right, now these next two are a little bit different. Reflecting over the line y equals -3. Well, remember the line y equals -3 is the line that goes through the y-axis. This being the y-axis, it goes through the y-axis at -3. So this is the line y equals -3. Obviously, a common mistake would be that people would make this line, so please don't do that. Anyhow, if we're reflecting over this, this time we don't necessarily have that same trick, but here's what we're going to do. We're going to count. Hopefully you can count. Here we're at 6, 7, 8, 9. If we are 9 above this point, then we're going to want to be 9 below this point if we reflect over this line. So 1, 2, 3, 4, and then we would want 5 more on top of that. And that would put us at -12. All right, so that means we've got +2, -12. All right. Next one, the line x equals 2. And so this time we're going to go through the x-axis at 2. So here's the x-axis, here's 2 on the x-axis, so we're going through the x-axis at 2. And, well, we're already on that line, and so we don't actually flip anywhere. We're just right back where we started. All right, and then of course we have the other one that we talked about, the other major line, y equals x. So this was x equals 2. We have y equals x. And remember this time we just switched them. So 2, 6 becomes 6, 2. And one more time you can see exactly why that's true. It follows both of those properties. This is perpendicular, and these two are congruent. All right, so there's some basics with just points. Here's an actual shape. So draw the image of triangle RTS after the reflection over the x-axis. So you can see, the thing that we're reflecting is in there. The thing that we're reflecting it over is right there. So x-axis would be this one right here. What we're going to do is we're just going to take each one of these points and reflect them, and then connect the dots when we're done. So if this one is 3 above, the reflection would be 3 below the line that we're reflecting. If this one is 8 below, then the reflection would be 8 above. If the reflection is 6 above, then the reflection would be 6 below. And let's make sure that we label our points here. So we got R prime, we got T prime, we have S prime. We connect these. And what we should see is a congruent shape just been flipped over your line y equals x. All right. Let's see. Here, we are proving, so this is learning target 4, proving that PQ, or P prime Q prime, is a reflection of PQ over line R. Sorry about the triangles there. I think this was originally a triangle and I switched it to a segment, so you can just cross those out. All right, prove that this reflection is an isometry. And so to prove that it's an isometry, we need to prove that these two lines are congruent, that they're exactly the same. And so here's what we're going to do. We are going to create an auxiliary. So first we've got, obviously, the given. And then we're going to create Q prime. And this is our auxiliary. All right, well, we know a couple of things. At this point, we see that we have two triangles, 1, 2. And if we can prove that these two triangles are congruent, then CP/CTC would get me these two sides congruent, which is what I want to prove that this is an isometry. So we've got a couple of properties in regards to reflection. I know that because this is a reflection, we'll say that this is point T. Because this is a reflection, QT is congruent to Q prime T. That would be the definition of reflection. And we also know that this is a right angle because it's perpendicular. So if we call this angle 1, call this angle 2, say angle 1 and angle 2 are right angles. And that would also be by definition of reflection. All right, well, because these are right angles, these are right triangles. So I'm going to say that triangle QTP and triangle Q prime P prime T are right triangles. That would be by the definition of right triangle, in that we had right angles. All right, well, now that we have right triangles, we only need two things to show that it's congruent. We've already got one side. We need maybe one more thing. And we can use our old friend, the reflexive property. So we can say that PT is congruent to P prime T. This is by the reflexive property. And because I have my two things and I know it's a right triangle, I can say that these triangles are congruent. I can say triangle QTP is congruent to triangle Q prime P prime T. This would be by, well, let's see, what are the two sides that we have? We have a leg and a leg. This is the hypotenuse. We don't know that yet. That's what we're trying to prove. So we have LL, which is one of our right triangle theorems that proves that triangles are congruent. And because we have this, we can now say QP is congruent to Q prime P prime by CP/CTC. And, well, because these two things are congruent, that proves that this reflection is an isometry. So we can say this is an isometry. And we can just say the image is congruent. All right. That pretty well does it for lesson number 2. Practice for learning target number 3 is here on 558, and practice for learning target 4. Just practice that proof, do it a few times until you have it mastered.